have him run a mile and a half. I'm going to time him. I'm going to plug that into a formula, and I'm going to estimate his VO2 max. You should be doing that in your lab. Okay, so I'm going to get an estimate. His VO2 max, I'm going to say, is 63 mLs per kg per minute. Okay, first of all, what do you know about that number? What does that tell you? What's your assessment? He's well trained. He's very fit. He's probably already a good runner. Okay, so I'm going to decide as his trainer, I want him doing his cardio workouts at 80% of his VO2 max. Okay, let's say he weighs 185 pounds. We did the speed formula in here last week, right?
Yes.
Okay, so I'm going to ask you two questions here. The first one is, how many calories will he burn in, let's say, 35 minutes at 80% of his VO2 max? And my second question is, what speed on flat ground to be at 80% of his VO2 max? Okay, I'm going to give you the formula, and I'm going to give you a few minutes to work on it on your own, and then I will do it with you. So this is the ACSM running formula, again, to calculate the submax VO2 at a given intensity. 0.2 times your speed plus 0.9 times your speed times your grade plus 3.5. Speed is in meters per minute, so you need to know the conversion. Miles per hour to meters per minute. You will multiply miles per hour by 26.8 to get meters per minute. Okay? So, did we do one like this where I gave you the VO2 max and told you to work at a percentage? Okay. See what you can do with it. Anybody have an answer for number one yet? 741.67.
Yes.
Unit?
8,085 minutes at 80% of his VO2 max.
Did you guys get this far with the speed? Okay, what does this mean? Why am I getting 234 for speed? It's meters per minute, so what do I need to do? Divide by 26.8, what do you get? 8.75, now this is miles per hour. Did everybody get that? Okay, we can't do 8.75 on the treadmill, we can do 8.7 or 8.8. Okay, because this is pretty darn fast, I would probably just put him at 8.7, even though rounding here would be 8.8, but judgment call, because this is speed on a treadmill, I'd be okay with either one. Okay, so everybody understand the concept and the math? Any questions? Yes?
I just have a question about the end. So we don't want it up to 9 or 8.5? It would just...
So we want it to be what you can do on a treadmill. So on a treadmill, you can do 8.1, 8.2, 8.3, 8.4. So if instead of telling you to do 8.7, I'll just round it up to 9. Just go ahead and do 9 miles per hour. That's 0.3 is a big deal, right? Between 8.7 and 9. So when we're just talking about math numbers in a vacuum, yeah, if we want whole numbers, I could round that up. But we're talking about speed on a treadmill, those tenths of a mile per hour make a difference. That's why I even rounded down, because even between 8.7 and 8.8, I'd rather be at 8.7. And you know, it's gonna get me pretty darn close. But I'd be fine with 8.8 here, but not 9. Okay, other questions about the math or about conceptually what we're doing? Okay, you gotta keep track of the VO2 max, the VO2 submax, the energy expenditure. Okay, you gotta know, common error here is to put the 63. Okay, I will never ask you to calculate speed at a VO2 max. It will always be the submax. Okay, you put 63 here. I will never ask you to calculate energy expenditure at a VO2 max. It will always be a submax. So make sure you keep track of your numbers. Okay, so Sebastian comes back to me and says, I don't want to run that fast today. I'm not really feeling it. I want to run 6 miles per hour instead. What do? I still want him at 80% of his VO2 max. If he's going to run 6 miles per hour, what adjustment do I need to make?
Increase the grade.
Increase the grade. So now, the goal of the VO2 is the same. I have a speed that I want. I got to solve for the grade. Okay, go ahead and do that one. And by grade, I mean incline. Everybody get this number? So what does this mean? We could write this as a 10% grade, which means he can run 6 miles per hour on the treadmill, but he's got to put the incline up to 10, which is pretty steep. Okay, so this is very high intensity, 8.7 miles per hour, flat ground, 6 miles per hour on a 10% grade is an equivalent intensity. He can do either one, he's going to be at 80% of his VO2 max. Equivalent intensity has an equivalent oxygen requirement. Okay, it's a high intensity because I gave him a very high VO2 max and then I put him at a high percentage of it. That's why these numbers are coming out so high. Questions before I move on? If you're lost, please ask a question. Because if you're silent, I have no idea that you're struggling. And I can't help you. Anybody lost on any part of it that I can help you with before I move on? Yes?
Why did you do the 6 miles per hour multiplied by 26.8?
Yes, so in order to plug it in here, it has to be in meters per minute, so I have to convert. So if you're given miles per hour, you multiply it by 26.8. On the last problem, we were solving for speed, so we ended up with meters per minute, and we had to divide by 26.8. So this formula and the conversion will be given to you, but you need to know how to use it. Anything else? If you have a question, you're probably not the only one. Okay, so now Sebastian's going to come to me and he's going to say, okay, but coach, I really want to run outside today. It's a beautiful day. So the issue with running outside is I can't control for your speed and grade, right? If you're on a treadmill, I know exactly what speed and incline you're at. If you're outside, your speed is going to vary. There might be hills, the incline's going to vary, and I can't track it as well. So I can use heart rate, because heart rate has a known relationship to oxygen consumption, right? As your intensity goes up, your oxygen consumption goes up, your heart rate also goes up. So if I know what percent of his VO2 max I want him at, I can figure out what percent of his heart rate max I want him at. Okay, it's not the same. 80% of VO2 max is not the same as 80% of heart rate max. It's not exact. It's a little bit different, so we have to convert. There's a formula for that. Okay? First, we have to know his heart rate max. In order to do that, we need his age. So let's say he's 22 years old. Do you remember the formula for heart rate max? Say it louder. 208 minus 0.7 times age. I will not give you that formula. You need to know it. Okay, so you're going to plug in 22 there. Please tell me what you get for heart rate max. Somebody else get that?
Yes.
What is the unit on this?
Beats per minute.
Okay, you have to have units on all your numbers. Now, this is heart rate. We're not going to be counting fractions of beats, so here we'll use whole numbers. So I'm going to say his heart rate max is about 193 beats per minute. Okay, so I want him at 80% of his VO2 max. I need to figure out what percent of his heart rate max that puts him at, and then take that percentage of 193. Okay, this formula is called the Swain formula. This is how you convert between percent heart rate max and percent VO2. Here's the formula. Percent heart rate max equals 0.64 times percent VO2 max plus 37. You do not need to memorize it. I will give it to you. You need to know how to use it. There are two variables in this formula, percent heart rate max and the percent VO2 max. If you know one, you should be able to solve for the other. The way it's set up is to plug in your percent VO2 max and solve for heart rate max. But if I gave you a heart rate max, you should also be able to solve for percent VO2 max using algebra. Okay, in this case, we know the percent VO2 max. We're going to solve for the percent heart rate max. What's the percent VO2 max? 80% VO2 max. That's what I decided as his trainer I wanted him at. Okay, for this particular formula, we don't put it in as a decimal. We put it as a whole number. That's just how the formula was developed. So I'm going to put in 80. So I'm going to do 0.64 times 80, and I'm going to add 37. Tell me what you get. 88.2. Okay, did everybody get that? Okay, so here's where we run into problems on the test, because there are so many steps that you're going through. If you're not following along with what you're doing conceptually, my question is, what will his heart rate be? What heart rate should he be at? That's the question I'm asking you. What heart rate should be at if he goes to do this run outside? You've gone through so many steps already. You get to this, and you say, well, I need a heart rate. I'm just going to throw a beats per minute on here. Is this beats per minute? Is it mLs per kg per minute? Okay, so I get people just throwing whatever unit they need, they throw on that. Which means you're not following conceptually what you're doing. What is this number? This is what percent of his heart rate max I want him at. Okay, but this is not what I asked for. I didn't ask you what percent of his heart rate max he should be at. I asked you what heart rate he should be at. So we're not done. What do we need to do? So I need to do 193 times 0.882. What does that give me? 170.23. Okay, I'm not concerned with a third of a heartbeat, quarter of a heartbeat. So I'm going to say, okay, Sebastian, you can do your run outside today. Try to keep your heart rate at about 170 beats per minute, which again is really high because he's very fit and I have him at 80% of his VO2 max. Okay, a runner can sustain 9 miles per hour for a long time. Do you understand the concept and do you understand the math? Go ahead.
When we answer that, do you want it to be like 170 beats per minute at 88% of his heart rate max?
That would be excellent. I don't think I'll require that if I'm just asking for what should the heart rate be. Because the question will be, what will the heart rate be for him to be at 80% of his VO2 max? So you can just put beats per minute on there. But I wouldn't mark that wrong because that would be extra information. Questions? Okay, let me give you another practice one. This one will be a little harder. Okay, so the next day, Sebastian comes to me and he says, okay, coach, I went for a run yesterday on the treadmill. I ran at about 7 miles per hour. Actually, I shouldn't have had this yesterday. Okay, I ran at 7 miles per hour on a 4% grade. First question, what percent of my VO2 max was I at? Second question, estimate what his heart rate should have been during that run. So you need the running formula. I'll write up here again. Did anybody get this? Okay, did anybody get something different or is stuck? Please let me know. What is the unit on this? And what is this, a VO2 max? This is the submax that he was running at that day. That's not my answer. Because my question wasn't what is his VO2 submax. My question is what percent of his VO2 max is he at? So what do I need to do? Okay, to find percent, it's always submax divided by max. Your score on the test divided by total points possible. So I'm going to do 47.77 divided by 63, multiply it by 100 to make a percent, and what do we get? 75.83.
83.
And this is, yeah, don't throw an ml per kg per minute on there. This is, he's at 75.83% of his VO2 max. Okay, so pretty close to where I want him at 80, but not quite there. Okay, see if you can estimate what his heart rate was during that. Everybody get the 85.53? What is the unit on this? Percent heart rate max. So now what do I need to do? What was his heart rate max? 93 times 0.8553.
165.
So I would estimate that was his heart rate during his run. I wanted it in 170. Use that 165. It's pretty close. Everybody get that number? Concept, math. Okay, so a lot of different ways you could play with this. He could come and instead of saying, hey coach, I ran 7.5 miles per hour in a 4% grade, he could come and say, hey coach, I swam yesterday and my heart rate was 150 beats per minute on average. What percent of my VO2 max was I at? You can figure that out. Because if you know what his submax heart rate was, you can figure out what percent of his heart rate max he was at. If you can figure out what percent of his heart rate max he was at, you can figure out what percent of his VO2 max he was at. Okay, I'm not going to practice with you all the different ways to play with it. Eric will probably give you some different ones. But if you don't have to memorize the formulas. You have to know how and when to use them with the given information, and keep organized because there are a lot of steps. Keep organized what your submax, what your max is, submax heart rate, submax VO2, max VO2, which formulas you're plugging in a whole number, which formulas you're plugging in a decimal, which formulas you need kilograms, miles per hour, meters per minute, concept, math. We okay? Yes?
What are the formulas you want to give us?
The formulas I will give you will be the ACSM running formula and the conversion to meters per minute and the swing formula. Those are the only formulas I will give you. So you need to know the heart rate max formula. You need to know how to convert pounds to kilograms. Any other questions on these calculations? Okay, I have another really cool calculation I'm going to show you. So, right now, you're sitting in your chair, been sitting there for a while. We can consider you resting. Are you consuming oxygen?
Yes.
Hopefully, yes. About how much oxygen are you consuming? Can you assign a number to that? 3.5. 3.5 what? Remember this? I said this is resting oxygen consumption. It's going to be important later. Here's where it's important. At rest, on average, you consume about 3.5 mLs per kg per minute. Milliliters of oxygen per kilogram of body weight per minute. Is it fair for me to apply that to everyone in this room?
Yes.
It is. We can agree that larger people are consuming more total oxygen. They have larger lungs, more blood volume, more muscle mass. But per kilogram, in a relative term, same for everybody. If we put your weight in there and convert to liters, larger people have a larger absolute number. Relative terms, it's the same for everyone. So, if we say you're going to stay in bed for 24 hours, all day, you're resting. So you're staying at 3.5 all day, we can calculate how many calories you'll burn in a day. That is your resting metabolic rate. Your resting metabolic rate is how many calories you burn in a day just to be alive, basically. Okay, I'm going to fine-tune that a little bit. So we can calculate that. We know how to calculate energy expenditure. Okay, we need the weight. So we're going to use 150 pounds because that's considered average, which is 68.18 kilograms. We're going to use 3.5 mLs per kg per minute because that is resting oxygen consumption. And we're going to calculate energy expenditure for a whole day, 24 hours. I want you to try to figure this out. There's one point where you will get stuck, and I want to see if you can figure out how to get through it. Anybody figure out what to put there? For minutes? For an entire day. How many minutes are in a day? 1440. How did you figure that out? There's 60 minutes in an hour and there's 24 hours in a day. So do 60 times 24. It means there's 1,440 minutes in a day. So if you stay at rest for 24 hours, that's how many calories you're going to burn. Let me know when you get it in. I'm not really concerned about an eighth of a calorie. So about 1,700 calories in a day. A 150-pound person stays in bed for 24 hours, they're gonna burn about 1,700 calories. That's resting metabolic rate. Resting metabolic rate is how many calories you burn in a day at rest. Okay, so you hear people always saying, oh, you have a fast metabolism, you have a slow metabolism. It's referring to how many calories your body burns when you're just sitting there. Okay, you can calculate this. All you need is your weight. Calculate your own. Okay, does everybody have their own number for the resting metabolic rate? Okay, so average resting metabolic rate, somewhere between 1,500 and 1,800 calories a day, which is why this 150-pound person, which is considered average, right in the middle of that range. So some of you will be in that range, some of you will be below that range, some of you will be above that range. It's completely, for this calculation, it's completely dependent on your weight. So that's the only thing that we're putting in different. The more you weigh, the more calories you're going to burn at rest. Okay? But this is an estimate. Okay? We're giving everybody to 3.5, which is an estimate. And then with your body weight, we're not differentiating between muscle and fat. And it does make a difference because muscle is metabolically active. It's burning calories when you're at rest and fat is not. So we can have a more specific measurement that's going to take into account how much of your weight is muscle and how much of it is fat. But that we have to go into the lab, have you connected to the respirometer and actually measure your oxygen consumption. Okay, so that's going to be a little bit different. This is an estimate. So what's going to make a difference in your actual consumption? Like I said, how much muscle mass you have. Muscle is metabolically active. So if someone is large because they have a lot of muscle, they're going to have the highest metabolic rate. Okay, which is why if someone's trying to lose fat, we want them to do resistance training and put on muscle. Because first of all, it improves body composition, right? Even if your fat stays the same, you increase muscle, that's an improved body composition, which you should understand from lab, right? And also, the more muscle you have, the more calories you're gonna burn at rest. So it's gonna increase your fat burn over longer term. It's gonna increase your calorie consumption longer term, okay? But if someone is large because of fat, they're also burning a lot of calories. Because the larger you are, whether it's because of muscle or fat, the larger you are, the more surface area you have. The more surface area you have, the faster you lose heat. So your body has to work harder to thermoregulate, which burns calories. So people who are large because of muscle have the highest metabolic rate. People who are large because of fat have the next highest metabolic rate. As you get smaller, your metabolic rate goes down. Okay, so that's where you sit in that range. Okay, but like I said, this is an estimate. kind of like if we were to take your heart rate right now. We could call it a resting heart rate, but it's not your true resting heart rate because you've eaten, you probably had some caffeine, maybe you've had some stress with this math, and your heart rate's elevated a little bit. So even though you've been sitting, there are other things raising your heart rate. So it's not your true resting heart rate. So same thing with this estimation. This isn't as low as you can go. As low as you can go is basal metabolic rate, which is a measurement. Okay, resting metabolic rate is an estimate. Basal metabolic rate is a measurement. So this would be the true lowest you can go, number of calories it takes for your body to stay alive for 24 hours. So to do this, you'd have to be hooked up to the machine that's measuring oxygen consumption. You have to sleep for 8 hours. Good luck as a college student. You have to fast for 12 hours because digestion raises your metabolic rate. You have to lie supine in a dimly lit, thermoregulated room so we can get you as relaxed as you can possibly be, slow down all of your processes, and then we measure your oxygen consumption. So it's going to be more accurate and it's going to be lower than the resting number. It's about 200 calories lower. So basal metabolic rate on average is somewhere between 1,200 and 1,500 calories per day. So 200-300 calories lower than resting. That number is important to have an idea of that number because that is the number of calories it takes for your body to survive for 24 hours, which means if you eat fewer calories than that, your body is starving. Right? You're not taking in enough calories to support life for 24 hours. You're starving. What happens in that situation is your body will hold on to its fat stores because fat is a very valuable source of energy and it will start breaking down muscle. Which is why if someone's trying to lose fat and so they starve themselves, hardly eat anything, 800 calories a day, you'll lose weight, but you'll lose muscle. The scale's not going to tell you that. The scale's just going to tell you, good job, you lost weight. That's why body composition is more important. You're not trying to lose weight, you're trying to lose fat. So you have to eat at least the number of your basal metabolic rate in order to spare your muscle. Hold on to your muscle and lose fat. You have to eat to do that. So that's an important number to know. Okay, questions on that? Yes?
You said it's about 200 to 300 less than what you
Less than what we're estimating for resting. Yeah. So you can do this calculation on yourself. Take off about 200 calories and assume that's your basal. Yes?
Can you explain that again when you were saying that it's you lose muscle, how that happens again?
Yes.
To the story?
So fat metabolism will slow to a screeching, I don't want to say halt, but your body's going to hold on to its fat and start burning muscle for energy to spare your fat to keep you alive. Yeah. So remember we talked about how glycolysis has to run, and if you're not eating, your glycogen stores are going to be empty. So the only place you can get that from is muscle. Okay, then hopefully there aren't too many days where you're just staying in bed for 24 hours, right? You're getting up, you're going to school, you're going to work, doing different things. So we have activities of daily living that we have to account for your typical day. Okay, so we call this resting metabolic rate plus activities of daily living. So you're going to work, you're going to school. If you have a very sedentary job, that's not going to increase much. If you have a very active job, you're very active throughout the day, your ADLs will add a lot. Exercise is even on top of that. So any workout is not even included in ADLs. That's on top of that. Okay, so resting metabolic rate plus activities of daily living is how many calories you actually burn in a typical day, right? Resting metabolic rate is how many calories you'd burn if you stayed in bed for a day. We include activities of daily living. This is how many calories you burn in a typical day. So average for this, 1,800 to 3,000 calories per day, depending on where your resting is based on your muscle mass and how active you are in a typical day. This is why our nutrition labels are based on 2,000 calories a day. It's right in the middle of the average caloric expenditure on a typical day. Questions on that? Those are numbers you need to know. The difference between basal resting and resting plus ADLs and the number ranges. Go ahead.
This is more just out of curiosity, but if someone, let's say, was at the resting metabolic rate, they were in bed 24 hours, but what if they were doing like a ton of mental work, like they were like on their computer, like studying or like...
It's not going to add significantly
Okay.
to
I wasn't sure how much
metabolic
the
rate.
brain burns
What
slowly.
might add to the metabolic rate in that situation is if something stressed you out and you had a rush of adrenaline, because adrenaline, remember, is epinephrine, which will mobilize your energy stores, which might cause you to burn a little bit more. But it's not going to be significant. Okay, so let's say, I'm just going to throw this in here real quick, because I like to talk about weight loss. If, let's say somebody has a basal metabolic rate of about 1,500 calories a day, meaning they can't eat less than that or they'll lose muscle. Okay, let's say they burn 2,000 calories in a day. Okay, so they're eating 1,500 and they're burning 2,000 calories in a day. So this is fine because they're eating enough to spare their muscle and they're at a deficit, 500 calorie deficit, so they're going to lose weight. That's fine. But 1,500 calories, not a whole lot. So if they want to eat more than this, they need to increase their output. Right? So if you increase your output and you're burning 2,500 calories a day, then you can eat 2,000 and still be in the same 500 calorie deficit. Okay? It doesn't matter if the calorie deficit is you're eating 1,500 and burning 2,000, or if you're eating 2,000 and burning 2,500, it's a 500 calorie deficit. Either way, the weight loss is exactly the same. Okay? So that's the deficit you want to have if you're trying to lose fat, but you've got to stay above your basal number. Good? Yes?
You said that you just have to stay above the basal metabolic rate to not lose muscle.
Yes.
Where does macronutrients
Macronutrients, okay, that's a great question. So weight loss and nutrition are separate. We like them to be in line. So here's the thing, and I'm going to talk about this again at the end of the semester. If this is your program, you're eating 1,500 calories and burning 2,000 in a day, it doesn't matter if these 1,500 calories are all coming from ice cream. It makes zero difference in weight loss, what you're eating. What matters is the balance. Ideally, we want to be in the deficit and have proper nutrition, but the nutrition does not affect the weight loss. Nutrition affects health and performance. We'll talk about that at the end of the semester. Awesome. Any other questions? Okay. So now, let's think back to where we started this chapter. This is a big chapter. We've been on this for a while and we're not done yet. So we started with, I introduced you to the term energy expenditure, which we said is calories, which we said is the measurement of heat. And then we talked about that's going to be either in calories or calories per minute for energy expenditure, right? Then we talked about direct calorimetry, which I already reviewed, so you're directly measuring the heat. What were the main problems with direct calorimetry that we talked about? Main limitations? Go ahead.
Equipment can produce heat and that's what we get.
Treadmill's also producing heat. The walls might be absorbing some heat. Your body's going to reabsorb some heat. There are limitations with that. So then we shifted to indirect calorimetry. And we said, okay, instead of measuring heat, we're going to measure oxygen consumption. So we're actually measuring oxygen consumption and carbon dioxide production. So we're looking at the ratio between the volume of carbon dioxide you're producing and the volume of oxygen you're consuming. That's what we're actually looking at. So there's carbon dioxide produced. this makes sense to you, yes? Okay, there's carbon dioxide produced here, there's carbon dioxide produced here, carbon dioxide produced here. You don't need to know how much. You don't need to know where they're produced. In 446, you'll need to know exactly which reaction is producing a carbon dioxide molecule and you know exactly how many are produced. For this class, you just need to know that carbon dioxide is produced in these metabolic systems. There's a known ratio between the carbon dioxide you're producing and the oxygen you're consuming. This is called the RER, which stands for respiratory exchange ratio. The ratio between the volume of carbon dioxide that you're producing and the volume of oxygen you're consuming. What's going to affect this is, bless you, what substrate you're using, carbohydrate or fat. Because you'll consume different amounts of oxygen and produce different amounts of carbon dioxide. Which substrate will have you consuming more oxygen, carbohydrate or fat? Fat. Because fat, you have to use oxygen to metabolize. Carbohydrates, you don't. So, think about this. If you're using mostly fat, this volume of oxygen number will be high. If the denominator is high, what does that do to the entire ratio? So if your RER is low, it means you're using mostly fat. If you're using carbohydrates, less oxygen consumption, RER is higher. Okay, so there's a range for RER from 0.7 to 1. If your RER is 0.7, it means you're using 100% fat. In 446, we derived this number. This class, I'm just giving it to you. If your RER is 1, it means you're using 100% carbohydrates based on the ratio of carbon dioxide you're producing to the amount of oxygen you're consuming. Is it possible to be at 0.7? Can we use 100% fat? No, why not? Glycolysis has to be running or you die. So we're always using a little bit of carbohydrate. So 0.7 is a theoretical RER. We can't actually ever be there. At rest is when you most rely on fat. Resting RER is like 0.8. Okay? As you increase your intensity, you shift to fast twitch fibers, you shift to anaerobic metabolism, you shift to carbohydrates. What happens to your RER? It increases towards 1. Does this remind you of anything? Intensity, substrate, carbohydrate, fat. So as intensity increases, we're shifting from fat to carbohydrates because we're shifting from slow twitch fibers to fast twitch fibers and therefore switching from aerobic metabolism to anaerobic metabolism. So low intensity is going to have a low RER, high intensity is going to have a high RER because of the substrate switch. These things are related. Yes?
What happens when the RER goes over 1?
I haven't gotten there yet. That's where I'm going. Other questions so far? So, remember when I first told you the relationship between oxygen consumption and energy expenditure, I gave you that number to convert, the caloric equivalent. What was that number? For every liter of oxygen you consume, you burn 5 calories. And I said, this is an estimate. It actually ranges between like 4.7 and 5.1. What that caloric equivalent is depends on the RER. So as you change substrate, the oxygen consumption relationship will change. That's 446 level material. Okay, in 446, you'll be calculating an RER, and then there's a table in the book that says if your RER is 0.9, your caloric equivalent is this. If your RER is 0.95, your caloric equivalent is this. Okay, right now I'm just using a 5. But what happens is as you get to the higher intensities, there are other places that produce carbon dioxide. Okay, So there's a known amount of carbon dioxide produced in the metabolic systems that gives us this ratio. At high intensities, there's additional carbon dioxide produced somewhere else, which I'm going to explain to you in a second. So if this number is abnormally high, RER goes above 1. So at very high intensities, you might have an RER of 1.1, which shouldn't be theoretically possible because we're already above 100%, we're already at 100% carbohydrates. So this means there's carbon dioxide coming from somewhere else, which is going to throw off our calculation. So our calculation at high intensity is going to be less accurate. That's the major limitation of indirect calorimetry. Okay, I'm going to say that a bunch more times, but let me tell you where the carbon dioxide is coming from. If you're working at a high intensity, what's happening to the pyruvate? Why does that happen? We activated PFK, sped up glycolysis, filled up the mitochondria, so the NADH dropped off its hydrogen and electron, reduced the pyruvate into lactate. So this lactic acid has hydrogen in it. We have to clear it because that hydrogen is going to cause fatigue. I gave you 6 ways to clear lactic acid. What are they?
Heart, kidney, muscle, same muscle.
1, 2, 3, 4, 5, 6. Okay. One of them was the buffer. And I said we'd talk about it later. It's later. One of the ways we clear lactic acid is called the bicarbonate buffer. It's called a buffer because it's buffering the hydrogen. So if the hydrogen is by itself, it's going to cause fatigue, which we're going to get to in the next chapter. If we connect it to something else and get rid of it, we're buffering it. Okay? So bicarbonate buffer, your body produces the bicarbonate buffer. Bicarbonate buffer is written like this, HCO3. HCO3 is the bicarbonate buffer. Its job is to buffer the hydrogen from lactic acid. So it's picking up the hydrogen that's in lactic acid. Where did the lactic acid get its hydrogen? From the NADH. Okay, bicarbonate buffer is going to pick up the hydrogen. It's going to become H2CO3, which is called carbonic acid. And then it's going to split. H2O, which is water, which is totally fine, actually good to have in your blood. And that leaves us with carbon dioxide. So this carbon dioxide is being produced outside the metabolic systems at high intensity, which is why at high intensity you will have an RER above 1, which makes our calculations for indirect calorimetry less accurate. Okay? Do me a favor, listen to this sentence the first time I say it. Don't try to write it down. I promise I'll say it again so you can write it down. The main limitation of indirect calorimetry is that it's less accurate at high intensities because of the carbon dioxide produced from the bicarbonate buffer, making the RER go above 1. Okay, so you don't need to understand why the RER going above 1 is a problem. It affects the caloric equivalent, okay, 446 level. You just need to know at high intensities, indirect calorimetry, these calculations that we're doing are less accurate because of the excess carbon dioxide produced from the bicarbonate buffer, making the RER go above 1. Okay, we call this carbon dioxide non-metabolic carbon dioxide because this is produced in the blood by the buffer. The other carbon dioxide was produced in the metabolic system. So these I would call metabolic carbon dioxide. This is non-metabolic carbon dioxide. Okay? Major limitation of indirect calorimetry is that it's less accurate at high intensities because of the non-metabolic carbon dioxide produced by the bicarbonate buffer. Makes the RER go above 1, which makes our calculations less accurate. Do you need me to say that again? Okay, this is why you should record. So you can listen to me say that as many times as you want. Okay, I don't want it to be a sentence, a word salad sentence that you memorize and have no idea what it means. Okay, I spend all this time explaining it to you so you understand the words I'm saying. Major limitation of indirect calorimetry. The problem with these calculations is it's less accurate at high intensities. High intensities, we're producing lactic acid, so the buffer is working. The buffer is going to produce carbon dioxide, which makes the RER go above 1. And the RER is what gives us our caloric equivalent. So it makes our calculations less accurate, which another way of saying that is those calculations assume that we're working aerobically. Right? The more anaerobic work we do, the less accurate those calculations are.
Oh, do we have to mention the non-metabolic?
Yes, non-metabolic carbon dioxide, and anytime you say the words bicarbonate buffer, you should write out that whole reaction. You need to memorize that reaction. And by the way, in 446, you spend a lot of time on this reaction, and you will do it in the other direction. This reaction is reversible. In 346, I teach it this way. In 446, they teach it this way. So you're going to see that reaction a lot. Questions? So we have major limitations of direct calorimetry, and major limitation of indirect calorimetry. And a lot of calculations that we worked on in between. One other important piece of information I want to give you about this carbon dioxide. This carbon dioxide actually has a very important function. Remember the very first class of the semester, I talked about sprinting up 3 flights of stairs with a backpack on and how you're going to feel at the top. We said your legs are going to be burning and your breathing rate is going to be elevated, and I said those two things go together. I'll give you the link later. It's later. This carbon dioxide, it's going to go through your blood, eventually go into your lungs, and you're going to exhale it. But as it's going through your blood, it's going through your brain. And there's a part of your brain that controls your breathing rate. We just call it the inspiratory centers. Carbon dioxide will activate the inspiratory centers in your brain to make you increase your breathing rate to help you blow off the carbon dioxide. Because blowing off the carbon dioxide helps you clear the lactic acid, right? So when you're breathing rapidly during intense exercise, it's not because you're trying to get oxygen in. It's because you're trying to clear carbon dioxide to clear the lactic acid, okay? So those two things will always go together. If you feel lactic acid burning in your muscles, your breathing rate will be elevated. Because the link is the hydrogen from the lactic acid. If you're at a high intensity, you're producing a lot of lactic acid, right? So the buffer's working, producing carbon dioxide, activating your breathing rate to help you clear it. Those two things will always go together. What system produces lactic acid?
Anaerobic.
Well, we have 2 anaerobic systems. Do they both produce lactic acid? Which system produces lactic acid? Glycolysis. Does the ATP PCR system produce lactic acid? No. So if you're out of breath, if your breathing rate is elevated, what system are you in? Glycolysis. Because the elevated breathing rate is from the carbon dioxide, which is from the buffer, which is from lactic acid. Okay? So what if I said you do a 10-second sprint and you're out of breath at the end? What system were you in? Okay, so here's the thing. You think because I said 10 seconds, automatically ATP PCR system. Can you sprint in glycolysis? Yeah. Let's say your top speed is 15 miles per hour. You can only hold that for 10 seconds. But you sprint at 12 miles per hour and you stop at 10 seconds. What system are you in? Glycolysis. Just because you stop at 10 seconds, you chose to stop at 10 seconds. If your top speed is 15 seconds, you can hold 12 12 miles per hour longer than 10 seconds. It's uncomfortable, but you could. Physically, physiologically. You chose to stop at 10. So just because you stopped at 10 seconds doesn't mean you're in an ATP PCR system. If your breathing rate is elevated, what system are you in? If your breathing rate is elevated, what system are you in? No, that was the correct answer. I just want you to say it again. If your breathing rate is elevated, what system are you in? If your breathing rate is elevated, what system are you in? If your breathing rate is elevated, what system are you in? Don't say I didn't tell you that. Doesn't matter if it's a 10-second sprint or a 5-second sprint or a 30-second sprint, 40-second sprint. If you're out of breath, you're in glycolysis. If you're in ATP PCR system, let's say you do a 6-second all-out sprint at your 2 top speed, you will not be out of breath after it. Nothing in that system is making you out of breath. Okay? So you need to know the bicarbonate buffer. You need to know that the carbon dioxide is driving the RER above 1. You need to know that the carbon dioxide is increasing your breathing rate. Okay, the other thing that increases your breathing rate is epinephrine. Does the same thing, acts on the inspiratory centers in your brain, increase your breathing rate. The more intense your activity, the more epinephrine you secrete, higher your breathing rate goes, more lactic acid